All right. Welcome to day 2, everybody. Today we're going to optimize. Today's going to be an optimal day. We're going to get things started with Professor Alan Captanolu.
Pretty good.
Captanolu?
Yep.
Professor Captanolu is a new assistant professor of mathematics at the Courant Institute of NYU. Did you cross paths with Antoine, or was he gone?
No, he was gone.
Working at the intersection of numerical methods, machine learning, and fusion energy. His focus is on exploring new optimization techniques and numerical methods for Stellarator and Coil optimization problems. He received a bachelor's in physics from Stanford in 2016, a PhD in physics from the University of Washington in 2021, and his last position was a postdoc at the University of Maryland with Dr. Matt Landreman. So let's get started. Thank you so much.
Yeah, thanks. Okay, so in this community we do a lot of optimization, and my goal today is to explain why we do that with Stellarators, why it's useful, and what all the jargon is of stage 1, stage 2, all this different stuff. So please stop me as I talk today. Please ask questions as I go along. These are slides originally from Matt. I've interspersed some of my own slides, and hopefully I'm just going to walk you through them. Let's get started. Okay, so I'm going to talk about optimization in general and introduce some key concepts, and then very quickly zoom into optimization for Stellarators. Talk about the kind of things we want to minimize, maximize, or prescribe for Stellarators. Like, for instance, we want to put flux substance typically. I'm going to talk about how we optimize for some of these big jargony terms you learned yesterday. And then I'm going to turn to what we call stage 2 in this field, which is trying to find coils and other current sources that actually produce these Stellarator plasmas in practice. And I originally had some slides for optimizing stability and turbulence. These are sort of more advanced metrics that you can optimize in the Stellarator. And I do have some extra slides on that. I've nixed it for now because let's see how short on time I am. It's a lot to cover already. Okay, so yeah, some basics in optimization. All optimization means is you have what's called a cost function, or you can call it objective function, loss function. You have some function that takes you from an n-dimensional space to a scalar, and we want to minimize some quantity. And there's sort of two primary ideas in all of optimization, which is if f has multiple minima, we say it's non-convex. So here we have some landscape. F of x is a function of x1 and x2. It's got some complicated dependence on those variables, and you can see it might have some local minima, and it might have a global minimum where it reaches its lowest value. So this f of x we would say it's non-convex. It's multiple minima. And then secondly, most of optimization is like a souped up form of gradient descent. You start somewhere on this landscape. You compute what's the gradient, and you go and minus that direction with some step size. So that means, like, let's say I start over here, I compute the gradient, which is that way, I go minus this way, I keep taking these little steps until I arrive down at a minimum. Okay? And okay, if I started over here and I did this, I took little steps, I would end up in this minimum. So one thing you'll find is when the objective is non-convex, these sorts of gradient descent methods or local methods, it doesn't guarantee you're going to get to a global minimum. In general, you're only going to find these local minima by taking these little steps downhill, basically. Okay, I wanted to also introduce some jargon. So there's a horrible jargon in this field, both in Stellarator and optimization. So you might see zeroth order method. That just means you are optimizing a function, and you're only taking evaluations of f on this landscape to actually do that algorithm. First order method, you're using f and its gradient. Second order method, you're using f, its gradient, and its Hessian. And most people don't go beyond that because already computing the Hessian takes a lot of time. So yeah, really don't think you should try like a 10th order method. This is a terrible idea. Just second order at most. Most popular methods like quasi-Newton methods are sort of like first order, and then they try and explain the Hessian to try and get some information about the second derivative of f. Okay, and then local optimization. Again, these are sort of the classical gradient descent type things where you start on the landscape and you take small steps trying to find local minima. And global optimization are a set of techniques that actually try and find the global minimum of the function in space. They come in all sorts of varieties, but generically you have to sort of more aggressively try and go around space and look for minima. You can't just take little steps downhill necessarily. Okay. Okay, so some other things we can do. We can always add constraints. We might have a set of quality constraints or inequality constraints. So that's all that G and H are doing here. And we might have not just one scalar function we're trying to minimize, but a whole series of them. And there's something called scalarization, which is a really fancy way of saying we take weights and multiply them all, and we just add them all up as one objective. And there is some like magic that goes into exactly what you assign these weights. They're sometimes also called hyperparameters. And exactly what the landscape of F looks like is going to depend on how all those weights are assigned. Okay, another common trick I wanted to mention is you can often turn a hard constraint that says G of X has to equal 0, into a soft constraint by basically adding it in the scalarization way, saying minimize F plus a weight times the magnitude of G of X squared. Because if you squint at this thing, this term is minimized when G of X equals 0. And so this is a way of sort of getting G of X close to 0, but not quite exactly prescribed. And often this is a easier problem to solve than the exact hard constraint. Okay, last thing I wanted to mention, this is a aside for the optimization inclined, but basically you can also do stochastic optimization, where you also want to control for random perturbations in your optimization variables. You basically sample from some distributions, some little perturbations, and ask, I don't want to just minimize a function, I want to minimize its expectation over some perturbations to variables. I'm gonna gloss over that. So yeah, I'm gonna skip now to talking about why we do this for Stellarator. Any questions right now on like these ideas and optimization?
Could you talk about what would be more useful, or I guess the benefits of using a second order method as opposed to a first order method?
Yeah, so generically, okay, all of this depends on exactly what you're optimizing. Generally, a second order method will be better in some sense because you're literally using more information about F. You have its Hessian information. So like in principle, if you have designed a good algorithm, it should do better. You have more information you can use. The reason we don't do this often in practice is because the Hessian can be very costly to compute. And so you don't want to have to recompute the Hessian every single iteration. Because remember, we're sampling F, its gradient, and the Hessian every time we take a step. So we start here, compute F, its gradient, and Hessian, and we keep doing that every single time. And that's really a lot of work each step. And yeah, that's the reason we don't do 10th order methods. Any other questions on optimization generally? Yeah.
Are there any kinds of like physical bounds on the error that you see in these calculations? Like I don't know. I was like thinking of like on like a length scale, like millimeter error. Like what kind of errors do you expect?
Yeah. So this is one of the reasons folks have looked at some stochastic optimization in this field. We find that, so imagine you build a stellarator, you design coils for it, and we find empirically, if you shift those coils by like a few millimeters in each direction, let's say randomly, you get like potentially very different looking field than you hoped for. And that's like one reason you might want to try something like this. You want to hopefully choose coils such that if there are some manufacturing tolerances, or like, it was not quite assembled correctly, you can still get a good looking plasma. But yeah, the question more broadly of like what errors show up in experiments, I'm not an expert in this. All I know is, yeah, things are sensitive, like millimeter level stuff can be important. That's one of the challenges of stellarators is the fields are very sensitive. Okay, sorry for the block of text, but I wanted to give some background on like why we do this for stellarator. So it's just talking about optimization generally. The point is, you probably saw yesterday for fusion devices, we want to design something that's steady state or quasi-steady state. That means basically designing an MHD equilibrium. And there are lots of physical quantities we want to describe or minimize or you name it. And but all these quantities are prescribed by the equilibrium MHD equations. So J cross B equals rho at P, and then subject to divergence of B equals 0, J equals curl B. Okay, so well, what can we do to actually minimize some of these quantities or prescribe some of these quantities? Well, in the case of the stellarator, we have a complicated three-dimensional boundary, and the solution to these MHD equations depend on the boundary conditions. So one thing we can do is like try and change this complicated 3D boundary to achieve these goals. That's the basic foundation of like why we do this stuff. Okay, this is a somewhat aside. This is like a slide of stuff that actually we don't typically optimize. We usually just describe this, and then we optimize the surface. But I wanted to sort of introduce some vocab. So there's something called the number of field periods. This prescribes a rotational symmetry to the surface of the plasma. So you can see it's field period number 3. It's got this 3-fold rotational symmetry, 4-fold, 5-fold. And usually that's just chosen beforehand. You say, okay, I'm looking for a NFP equals 4 stellarator, and then you let that boundary change, but subject to that 4-fold symmetry. Same thing with the number of coils. I'll show that in a second. So typically, you choose. You say, I want 40 coils all the way around, and then those coil shapes are allowed to change and move in space, but the number of coils is fixed. In principle, you don't have to do this, but optimization gets a little more complicated if you don't prescribe these integers. Okay, and then a couple other choices for coils. Again, we'll talk more about core optimization near the end, but I don't know what the same thing as okay. So one choice for the coils is how are they topologically linked with the plasma? So are they colloidally, helically, or not linked at all? You can see here some options. So the red coil here is like helically linked with plasma. The blue coil is actually not topologically linked at all. And yeah, there's many choices. I'll show you some more options in a few slides. And yeah, same thing with the mod B contours. This is related to quasi-symmetry, and I'll show some pictures of this later. Okay. All right, so yeah, we have some idea of what optimization is. We have some reasons why we might want to do this for stellarators. And given minimize f of x, we need to tell you what f is and what x is. So first, what is x? What are the variables that we're actually trying to change in order to minimize some objective? What we could do is we could say X are the shapes of the coils. And what we do is we change the shapes of the coils, we recompute those fields, and we get a plasma surface that's self-consistent with those coils. This is called free boundary MHD. It's extremely challenging in 3D and really, really fragile. So much of the space is very bad. It's hard to get good flux surfaces. And yeah, this is just a really challenging thing to do. This is basically trying to do the full self-consistent problem of optimizing the coils and the plasma at the same time. Okay, so for a long time, we have not really tried to do this or have had sort of limited success with it. Another thing we can do is actually just consider the plasma for a second. Take X as the shape of the plasma, the three-dimensional shape. You can parameterize that shape with some parameterization, which I'll show in a few slides. And yeah, this tends to be quite a bit more reliable. It turns out you're actually solving a slightly different problem here called fixed boundary equilibrium. And that tends to be better behaved, easier to optimize. And yeah, this is typically what we do nowadays. And you'll see in a second, what we're going to do now is like solve this problem for the plasma, and then we're going to solve a second problem for the coils. So this problem is going to be called stage 1, sorry for the jargon. And the second problem where we figure out what coil should go with that plasma, it's going to be called stage 2. And yeah, there are other options here. So you can do what's called single stage and take the degrees of freedom as both the shape of the plasma and the coils. It's a little complicated to explain, so I'm going to gloss over this. And there's also some semi-analytic solutions called what's called the near-axis expansion, and that takes the degrees of freedom as the shape of a magnetic axis. So there's other ways you can formulate these problems depending on what you're trying to do. Okay, so yeah, as I mentioned, the way we found tends to be most robust is we split up these problems into stage 1, where the parameters are the shape of the plasma surface. We change that shape and we try and optimize some physical objectives. I haven't actually told you what any of those objectives are, but we'll get to that in the slide. And then we have a stage 2, which is we have found a good plasma, good stellarator shape, and we're going to fix that, and then we're going to find coils that actually match that shape in practice. Okay, and the objective there is going to be the error in the normal component of the B field on the shape we found during stage 1. And there's a quick way to see why that is what we want to target. So if you consider a low pressure plasma, so J is curl B is roughly 0. Then because the curl B is 0, we can write scalar potential phi for B. Now the divergence constraint for B gives us a Laplace equation phi. And all of this is subject to a boundary condition B dot n equals 0. And this is just Laplace's equation with the Neumann boundary condition. There's a unique solution. So what's important about this? What's important is that the boundary condition is B dot n is 0 on the boundary. And so if we're able to find coils that basically get us B dot n is essentially 0 on the boundary we found in stage 1, then we're good to go. We found coils that have matched the plasma we designed in first stage. Moreover, this also tells you that the shape of the toroidal boundary surface plus some extra parameters, if you have pressure and current and are given the total magnetic flux, that determines the magnetic field everywhere inside the plasma. And this fact that the shape totally determines it allows us to basically just have the coil optimization target this B dot n on the surface. Okay, and here are some examples of some stellarators. think you talked about W7X yesterday, but you can see these plasmas and these coils get very complicated very quickly. Okay, so I've told you what the X variables are, the variables for optimization for Stellarator. What are some of the objectives that we're actually trying to minimize or prescribe in Stellarator? And you talked about some of these physical quantities yesterday. So one is we want closed nested field lines, magnetic field lines. Chaotic field lines are bad. They let the plasma like really mix around from the cold edge to the hot middle. So we generally want to avoid chaotic magnetic field lines. And so these sort of nested surfaces would be good. These sort of chaotic field lines would be bad. And the way we describe this in general is we often put this in as a constraint when we solve for MHD equilibria. We say, give us back an MHD equilibria that has nested flux surfaces by construction. So that's a big one. A sort of side note on that, you can often characterize these or look at these surfaces with the Poincare plot. Basically, you take your three-dimensional torus, take a cross-section, and you look at field lines, and you let them just make punctures on this cross-section every time they make a toroidal transit. And that gives you, if you do a lot of toroidal transits, that gives you plots like this, where you see nice nested surfaces here. And if you have more complicated topology of the magnetic field, you might get magnetic islands. You can see these islands on the outer edge, and you might get full chaos where there's no sort of clear structure to where the magnetic field line will arrive at when it punctures again. Okay, so another thing we often target is called the rotational transform. Not only we might target a particular profile of the rotational transform in the plasma, but we also want to avoid certain rational numbers of this quantity. You can ask me if you like why that is, but basically it's related to where islands pop up in your magnetic topology. And yeah, there's some sort of trade-offs here. You might want high magnetic shear because it actually makes the islands thin. And lots of different stellarators have chosen different profiles for rotational transform. So this is looking at the distance from the magnetic axis to the outer edge of the plasma. And you can see a lot of these devices were optimized to avoid the rational surface at iota equals 1, I equals 1/2. And LHD just says, no problem with islands, but they're going to make the gradients of the rotational transform very large and hopefully make those islands thin. Good. Okay, so some more details about what larger rotational transform does for you. But point is, this is something you typically want to target and think about when you're designing a stellarator, and one of the main things we optimize for. Okay, and then we have a big one for stellarators, which is quasi-symmetry. So you probably have seen yesterday talking about trapped particle trajectories. And we have these different classes. We have toroidal quasi-axisymmetric stellarators, where you can see this trapped particle basically bounces between these toroidal contours of mod B, and it's slowly drifting toroidally around the device as it bounces, right? Same thing with the quasi-helically symmetric. It's bouncing between B contours that form like a helical ribbon and slowly helically going around stellarator. And lastly, with QI, or in this case, quasi-colloidal symmetry, it's bouncing between two colloidal contours of mod B and just wrapping around colloidally as it drifts. So you should have talked yesterday on why these are important for stellarators. They guarantee certain confinement properties. So this is really important to target when you're designing a stellarator in the optimization. Okay, and this is just to say we've gotten really good at this. So since 2021, I should explain this for a second. One way you can directly measure how good your confinement is in a Stellarator is you take your optimized boundary and you literally just do Monte Carlo and like spawn some fusion particles in your device and look at how long do those fusion particles just like stay in the device. Okay. And so this is telling you how many alphas basically are lost after you have simulated it for a long time. And basically, we've gotten it down to essentially zero, few percent. And all of this has been since 2021. So there's been a lot of progress on getting really, really quasi-symmetric stellarators optimized. Okay, so a little more detail on how that's done. So I mentioned in stage one, what we do is we take the a description of the boundary and we try and optimize those parameters. The typical thing we do to describe this 3D toroidal shape is we write it as a Fourier series in both directions. And this might look like a little bit of a funny Fourier series, but that's because typically these devices are built with two discrete symmetries in them, called stellarator symmetry and this field period symmetry. And so that's why it's a little bit different than like the normal double Fourier series you might see. But that's essentially what you're looking at. So this is just a convenient choice to parameterize 3D torus. And what's important now is that we have some coefficients of this parameterization, CMN and RMN, and these become the parameters we can optimize that change the shape, and we can use those to minimize some objectives. Okay, and in general, we're going to have 2n plus 1, 2n plus 1 optimization variables from this double Fourier series for the surface of the plasma.
Actually, I have a quick
Yeah,
question. So lowercase m and lowercase n there are the colloidal and toroidal node numbers, correct?
Got it.
Uppercase M, uppercase N are just those are those related to the
So yeah,
user coefficients for yesterday, or
no, I should have fixed this. So this is just the largest colloidal number and the largest toroidal number. So instead of 5 here, imagine it's m and n.
gotcha.
Big m and n. Good. Yeah. Any other questions on like the setup here? Okay, and we're interested in quasi-symmetry. One of the things you might have learned during the quasi-symmetry discussion is that perfect quasi-symmetry means that there's a coordinate system where mod b is actually a function of just 2 variables. So it's sort of restores the confinement that you were hoping for when you had full axis symmetry. This coordinate system, this sort of combination of the angles is called Boozer angles. And so traditionally people have optimized for quasi-symmetry by sort of trying to sort of make mod b look like this and penalize deviations from it. What we often do these days is a little bit more complicated looking. It's some rather horrible looking combination of b and psi and other things. I'm not going to go into this. But the point is, this is an effective way to basically minimize deviations from quasi-symmetry. And this n appearing here is sort of your choice that you made for the field period symmetry of the device. Okay, and typically for, let's say, this polyhelical device, you do want to add some more terms to the optimization. So in this case, you can add a target aspect ratio for the device to the optimization. And you might add more terms like you want a particular iota, a particular rotational transform, or you want to avoid a certain rational number of rotation. Okay, so sorry for another big block of text, but I wanted to show you like the explicit problem for a second. So all of this I've told you for stage one kind of gets quite complicated looking when you put it together. So you have to give pressure profile and a toroidal current profile. You need to have a MHD equilibrium code that can tell you, given shape of the stellarator, what's the equilibrium. So you need that. You need an optimization algorithm that can actually do the optimization we're trying to do for stellarators. And then you need all your objectives that you're interested in. And if you have many objectives, you have to put weights on all of them, which here they're listed as sigma I. Okay, so these are all the weights of all the objectives you have. And then what do you do? Well, you start with some RMN and DMN. You just fix some parameters, some reasonable initial starting guess for the boundary, and then you compute the equilibrium of that from that boundary and from the profiles that you gave, and then you evaluate your objectives from that equilibrium, and then you just keep doing this. You then change the surface a little bit. You recompute the equilibrium associated with that. You recompute your objectives, and you keep doing this. Keep trying to minimize your objectives. Okay. And typically, again, this is done with like a gradient descent type thing. So you're trying to slowly take steps to minimize these this total objective. Okay, that looks bad enough, but some reminders here. So in order to do the part where you get an MHD equilibrium, you need a MHD equilibrium code. This is non-trivial. These codes are quite complicated. This includes VMAC and DESC. You can see DESC in the lecture after this one. And that also slows down the optimization. Every time you change the shape, you have to recompute the full equilibrium associated with that shape. Moreover, and this is a bit advanced, but the problem is very challenging. It's a non-convex landscape, and it's got lots of these bad shapes where like it's hard to find an equilibrium with closed flux surfaces. And so in practice, we do something called continuation methods or Fourier continuation, which means actually what you do is you start at super low resolution, like just one or two modes in describing the boundary. You converge that problem, get a solution, and then you use that as an initial guess for 3 modes in each direction, and you converge that problem, and then 4 modes, and you sort of take this staged approach where you're solving sub-problems until you get higher and higher resolution. Yeah.
So 2 questions. Like, so first, how do you find an initial boundary shape? Like, what's the initial shape general?
Yeah. There's no there's sort of like reasonable choices, but this is the choice. Yeah. It's there's no description here. For designing QA stellarators, a reasonable initial guess is start with tokamak, start with the axis symmetric thing. But yeah, this is just like you have to try some stuff.
And the second question was like, when you're doing that Fourier continuation thing, are you guaranteed to be finding your most optimal shape?
Definitely not. Yeah. That's true whether or not you do the continuation. This is a very non-convex problem in general. And that means with optimization algorithms, you're not going to find the global minimum, the best stellarator. You're going to find hopefully a good stellarator somewhere. You're going to find a local.
So the point about continuation method is as soon as you increase M and N, more local minima appear, so that it's more difficult to.
Yeah, so that is the story. Is that directly optimizing with say like 5 modes each, the space is very complicated. There's lots of local minima, and it's hard to like find anything that's any good. I don't know how true this is. I'm not sure anyone's looked at it like super closely, but this is the sort of story that's told. And indeed, if you try and just directly optimize with lots of modes at first, you'll get a poor solution in general. This continuation does tend to help get you much better much more quasi-symmetric solutions. Yeah.
And that does it help reduce with low resolution eminent like a global scan of your parameter space as is smaller, and does that help to find where possibly the global minimum is?
Yes. So there are. I believe there are. The space is nicer in low resolution. So there's less local minima to worry about. And unfortunately, the problem is worse than I've been describing, which is even at low resolution, you find that some shapes, it's still challenging to get a MHD equilibrium with closed flux surfaces there. In other words, VMAC, you might change the shape a little bit, and suddenly VMAC will tell you it failed and did not find an equilibrium with closed flux surfaces. And then your algorithm just has to backtrack and go back to where it was. Yeah, okay, there's a long story there, but maybe we should move on, and I'm happy to talk more about it at the end. The short story is that the space, even in low resolution, is quite a complicated thing. Okay, so this is just some nice pictures showing, in this case, a 2-field period quasi-axis symmetric device. You can see the quasi-axis symmetry because if you look at mod B contours, so this is mod B contours on the surface of the plasma. And then what you're doing for each of these is you sample one of the interior surfaces until you get to S equals 1, which is the actual boundary. And you unravel the torus into the angles phi and theta, and look at the mod B sort of that phi theta plane if you like took the torus and like flattened it out. Right? And what you should see with quasi-axis symmetry is basically this this band across the toroidal angle. Okay. And not only is it satisfied, you can see well at the boundary, it's satisfied extremely well at different interior surfaces in the plasma. So it's throughout the volume. Okay, same thing for this. This is a 4-field period QH stellarator. You can see the QHness through these sort of like helical mod B contours. And again, it's well satisfied throughout the volume. I haven't really talked much about QI, quasi-axis generic configurations, but there's been a lot of progress in this too. So with different field periods, different designs, and yeah, I'm gonna gloss over this in particular interest. Okay. So yeah, I'm gonna move on now to talking about stage 2, how you design coils. And maybe I'll just pause for a minute, see if there's any last questions on the first part.
Wait, if you just go back to that graph with all of the like different, like it was quite a few slides before, like all the different papers and the designs that they had. And the,
Oh yeah.
Wait, how are they doing better than Speed?
Yeah, I mean we've gotten really good at this. Maybe Matt has a better answer.
The question was how is it better than Eater?
Yeah.
So this has to do with something Elizabeth talked about yesterday, how in one of the differences between QA and QH is that the banana orbits are thinner in QH.
Hmm.
So the losses that are there for Eater are basically because a tokamak is QA.
And notice all these are QH,
so the orbits are kind of wide, and the 1% or so of losses there are just from the alpha particle banana orbits being fairly wide. If you make a QA or QH with the same minor radius, like there's a sort of effective, ratio of the banana width to the device size is smaller, same in the strength minor radius. So that's why I define this better in QH.
Yeah, agreed. It's pretty amazing.
Also an A, but A is a subset of QA.
Okay, So let's move to coils. So first, there is once again a ton of jargon in this field, so I wanted to add a little jargon definition. So there's lots of different names for coils. Coils, big coils above and below your plasma are called vertical field coils. Why is that? Well, if you drive a current in this thing, it mostly provides a B field that is vertical. Okay, big vertical B field through the plasma. So modular coils are coils that basically are pretty tight to the plasma surface and just interlinked with it once. Helical coils, you can see they interlinked multiple times and sort of helically wind around. Yeah, I could talk at some point about sort of what are the trade-offs of some of these coils, but let's do the definitions first. Coils that are topologically unlinked, we sometimes call saddle coils, sometimes we call these dipole coils. Yeah, there's sort of mix used there. And then we can also try other stuff. I think you probably talked about Muse yesterday, and Muse was a tabletop stellarator here at Princeton, where they designed a stellarator that just is shaped by these permanent magnets in an array on the outside of the plasma.
I don't think we've talked about it much else, but did we?
Oh, I don't know. Kenny didn't talk about it?
Mike C will talk about it tomorrow.
Oh, okay,
Yesterday
great.
was CNT and W7X.
Oh, okay, great. Good. Okay, so you'll hear more about this. This is a really fun thing to do for tabletop experiments. Okay, I'll leave it at that. Okay, so I want to also sort of put this in context, which is that I told you before the goal of coil design is going to basically be match beta n on the plasma surface that you designed in stage one. And one way you can do that is basically you parameterize the magnetic field by some parameters that are associated with your coils or your magnets or whatever you're designing to produce the magnetic field. And you try and minimize this beta n quantity squared on the plasma surface. And if you minimize that thing really well, it's going to be essentially zero on the plasma surface, which means you found coils or current sources that match the plasma you got in stage one. Okay, and this generic kind of problem where you have a given desired magnetic field on some surface, in this case, a toroidal three-dimensional surface, and you're asking how do you find current sources to provide that field. It's called inverse magnetostatics, and it comes up all over the place, and there's lots of degrees of freedom in principle. How many current sources, where to put them, what shape should they have, and what strength should they have. So there's lots of free things to play with. And moreover, in this beta n, in this objective we're going to minimize, this magnetic field is coming from the coils or whatever current sources you're using. And to evaluate those, you need to do the Biot-Savart law, which tells you how currents give you magnetic fields. And so this is also potentially going to be somewhat expensive unless you do some tricks because you have a double integral and potentially a triple integral. And so yeah, if you're not clever, that's a lot of numerical work with a 5-dimensional integral. So keep in mind. Okay, some other sort of rough advice about this. You can think about finding coils as sort of analogous to fitting data with a polynomial. Just to remind you what that looks like. So if I start with like a degree 1 polynomial and I have some data in these circles, degree 1 polynomial will give me some fit that looks like this. Sorry, the blue line here. And then cubic will give me a slightly better fit, and I can keep, adding polynomials of higher order to get a really good fit to the data. But the problem is what's called the condition number is getting really, really big. What that means is you're sort of starting to overfit to the data, and your fit is getting very, very sensitive to exactly what the data points are. Okay, so this is sort of a generic problem where you can use more and more in this case, higher degree polynomials, but you do that at the expense that the fit gets like more and more sensitive and sort of a little bit more dangerous when you get new data. So typically you want to sort of balance this. You want to do a high enough degree to get a good fit, but you don't want to do like super high and just like completely overfit the data. And yeah, this hopefully will be clear in the coil context in a second. Good. Okay, so as the polynomial degree increases, fit is closer to the data but less regular. The polynomial degree in this case is what we call the regularization parameter. Okay, so in the context of coils, one kind of regularization is needed to basically avoid these kind of solutions. What's interesting about this is you have a perfectly good coil set. And what I can do is I can take a piece of this coil and bring it all the way out and bring it all the way back in along itself. Those currents, the magnetic field associated with those currents will basically cancel each other. So these set of coils will produce essentially the same magnetic field as these sets of coils. But ideally, I don't want this like little path of currents that does nothing, makes my coils way longer. But they produce the same field. So how do we actually avoid this when we do coil optimization? Well, we need to do what's called regularization, similar to this polynomial bit. And actually, you can think about this fact that like very different coil designs give you the same field as, in a sense, a good thing. What this means is you can like add a lot of requirements on your coils, and still you might be able to find coils that can satisfy all the requirements of like getting the right plasma, but also you can prescribe the coil curvatures, the coil lengths, the coil torsions, the number of coils you want. All this stuff sort of gives you a little bit of space to work during optimization. Okay, so now I'm going to talk about specific methods. One is called the current potential method. It's in this code called red coil. And the idea is you consider a sheet current on a coil winding surface. All that means is I imagine that there is some toroidal surface in green that sort of surrounds the plasma. And I let a current, continuous current just be on that green surface. And I ask, what should that current look like to match the plasma that I designed in stage 1? Okay, so what's nice about this problem? What's nice about this is that if you have this surface current, you can actually write it as the normal cross gradient of the current potential. And this has a nice structure when you solve this problem. So to remind you, so now what we want to do is we want to choose this current potential. We want to minimize its distribution on the on this winding surface in order to match the plasma surface. So get the thing we got in stage 1, it's the B field there. And then in order to deal with this regularization issue, we add a penalty on the total magnitude of the current on the surface. And this is basically a weight that tells you how much you should penalize really big currents. Okay, so this is going to avoid like terrible, unrealistic solutions where like it perfectly matches the plasma, but the current on the surface is like 100,000 mega amps or something. It's like totally unrealistic. And you can get those kind of solutions because otherwise, without this thing, you're just going to overfit the plasma as much as possible. It's going to give you as large currents as it needs to try and match the plasma. Okay, this is really, really nice because if you actually write down this term in terms of the current potential, you'll find it's actually a linearly squares problem. Linearly squares is convex. That means it just has one global minimum, and we know how to find it. So this is really nice. And there's only 2 parameters here. There's a where do you put the winding surface, and then there's this regularization parameter. Okay, and then it has some downsides, which is at the end of the day, you don't want this continuous sheet current. You actually want to cut cut it into like discrete coils that you can actually build in the real world. And you're going to have some errors when you do that. And you also are neglecting this third dimension. You're restricting it to lie on a surface, when in principle, you kind of want the coils to be able to vary continuously in 3D space, take advantage of the full three-dimensional space to minimize your objectives. Okay, I'm going to skip past. This is just a quick slide showing as you change lambda, you get very different solutions. Okay? So if you have lots of regularization, you get simple coils, you get a simple looking current potential in this phi theta space, but you get very high errors in the field on the plasma you're trying to match. And similarly, if you turn down the regularization, you get more complicated coils, but you get a much better solution on the plasma surface. But the current potential got a lot more complicated.
Is there any way to build in optimization for the winding surface that would reduce the current potential that could have like more beneficial properties?
Yeah, I think a few people have tried versions of this. I think Elizabeth has a paper where she lets like sort of optimizes over where to put the winding surface in addition to like solving it each time. So there are methods you can do there that do help, yeah. But that also complicates the optimization problem. And one of the big advantages of this method is it is easy to solve. It's linearly squares. Okay, and here's sort of a more modern method, which is called filament coil optimization. This is you basically directly parameterize a coil as just an infinitely thin curve in 3D space. You parameterize that curve x of t. Once again, we love Fourier series up to some number of terms. And you do this for each of the variables, x of t, y of t, and z of t. And you just now have these parameters, these coefficients appearing in the series, and you let those vary and change the shape of these coils, and also change the currents that go through these coils, and use that to optimize the magnetic field on the plasma surface. Okay, so yeah, once again, want to match the magnetic field, normal component of the magnetic field on the plasma, and then we might add more regularization terms. In this case, it really is important to, for instance, penalize the length of the coils, because these will really have the problem we showed a few slides ago, where you can always take these coils, stretch them to infinity, and stretch them back, and it will give you the same field. And so we need to sort of penalize the length to sort of promote solutions that don't have these weird offshoots. And then typically there's many other things you want to add here. Like you don't want coils that are like super close to the plasma. You don't want coils that have super high curvature. So yeah, the ... the list goes on and on and on. Things you can add here. And unfortunately, each of them comes with weights. Typically, we manually tune those weights. There's a lot of work to be done. Okay, there's clear advantages here. They represent sort of realistic coils a little bit more. It accounts for the discreteness of coils. The problem is the optimization is much harder. It's non-convex. As you add more terms, things just get more and more complicated. You have more weights to play with. And it does benefit because of this from good initial guesses. And in fact, sometimes we often do this Fourier continuation again, where we optimize each of these coils with some low number of NF modes here, converge those coils, add a few more modes, and sort of keep solving subproblems. But this is, I don't know how common this is. It's useful sometimes, but yeah, I don't know how often it is. Okay, so this is basically wrapping up here. So to summarize, there's lots of degrees of freedom in the shape of the Stellarator. We can use this to achieve really important physical objectives in stage 1. I'm just going to go ahead and list these. I didn't have time today to talk about some of the more advanced things, like using it to promote MHD stability, using it to reduce turbulent transport. But these are sort of like ongoing work in the community. So I do have extra slides if you want to talk about this. But yeah, unfortunately, the list for both stage 1 and stage 2 just keeps on going. There's always more stuff we want to optimize, prescribe, get the best Stellarator performance we can get, and to get the sort of simplest and most buildable coils we can hope. Okay, so I will also mention some open questions. So one of the things folks have worked on in the last few years is how to combine the two stages. This is called single stage, and there's been a lot of progress there, but there's still a lot of work to do in optimization because these are really complicated optimization problems. You might have like 15 objectives you're trying to minimize. They all have weights on them. You need really good initial guesses to like get something useful out of it. So this is ongoing work. We talked a little bit about stochastic optimization, which is how we sort of try and find configurations that can tolerate if you have manufacturing or assembly errors when you actually try and build these things. And there's lots of other stuff. How do you do global optimization in spaces? How do you optimize when your objective is actually not this like smooth function in space, but actually is like super noisy and terrible. It's very hard to deal with that with sort of traditional local algorithms. And yeah, how to balance multiple competing objectives, how to optimize some of these parameters that typically we fix right now, like the coil topology, the number of coils, the field period. There's certain integers that we just fix and don't let vary right now. And at the end of the day, we're really just there's a lot of optimization work to do and a lot of interesting work still to be done to find good Stellarators and simple coils that hopefully can sort of provide the basis for a new exciting Stellarator design in the next few years. Okay, thanks everyone.
Got a few minutes for questions. Online, please raise your hand if you have any questions. We'll start taking them out. You want me to just signal?
Okay, sure.
Yeah, so I think back on slide 27, you were comparing like overfitting. And I know that you talked about having the optimization parameter to, I guess, prevent that overfitting or punish excess complexity. But if you optimize coils to a certain equilibrium, to a certain MHD equilibrium, is it still, I guess, equipped to handle like perturbations to plasma shapes?
Yeah, so in general, no. So what we do find is that so we're targeting the like beta n squared on the plasma surface. Mm-hmm. And in practice, we don't find coils that perfectly give you beta n at 0. Mm-hmm. There's always some error on there. And typically we can tolerate a bit of error. A bit of error does mean that when you build this thing, the plasma surface is going to be slightly different than where you had planned it was going to be. Mm-hmm. But you can actually check once you have coils, you can do a self-consistent calculation at the end, check directly like do Poincare plots, mm-hmm. and just check like, okay, is my plasma surface roughly still the same shape? I still have good surfaces, I still have good quasi-symmetry. Mm-hmm. So often we sort of get the coils to give you a low enough error that when you check the field with those coils, you can actually see, okay, I didn't like totally mangle my plasma from stage 1. Yeah. It's quite close. It's still giving me like a good solution.
Gotcha.
But this is a really important part of after stage 2, you need to check, is it good enough that my stage 1 plasma is still basically the same?
Okay, gotcha.
Okay. So I was thinking about this analogy. So in this analogy, the problem is that the condition number grows. Yeah, I assume that is because you're teaching a high order polynomial interval. And would you, for this analogy, you could just slice your domain and use a piecewise polynomial? Can you do that for coils too? Something similar.
Yeah, so don't know where this analogy breaks down.
That kind of doing the Fourier multi-grid stuff, like
yes. I mean, that's true. That's a pretty good. That's somewhat an analogy for this Fourier continuation, right? You're sort of starting with a low order description of the coil, converging that and then trying to go higher and higher order. But yeah, I'm not sure how far the analogy goes. In the case of this linear least squares problem, so this is the problem we solved for the current potential method. There is a direct sort of analogy, which is that what's important here is the condition number of this matrix A transpose A, and as that condition number gets really bad, this inverse gets really bad. So you'll start getting like totally crazy solutions with like super high currents and stuff like that. I think you've been waiting that for.
So on this linear least squares problem, I think I'm a little confused. I don't know if like this slide was a analogy like you were saying. Like, do you guys use you've been mentioning that you use polynomials as your like basis functions for this. Do you use polynomials in practice, or are you using more like cylindrical Fourier series?
Well, yeah. So for the filaments and for the plasma surface, we use Fourier cosines and sines.
Yeah.
Not like x squared and stuff. Okay. Yeah, I mean, there's still problems. You still have to be careful about this trade-off between regularization, these Fourier continuation methods, like how many modes do you really want? But yes, it's a little different than polynomial fitting. And unfortunately, there's a whole like literature and many textbooks written on like polynomial versus trigonometric interpolation and what are the trade-offs, and who wants to say that? Question. Yes, yeah.
Yeah, so in terms of actual minimization methods, I know I've seen a lot of people use like specifically like LBFGS, and I was curious if you could say like why people tend to use that method, or if there's other ones that like historically yielded pretty good results as well too.
Yeah. Right. So for some context, so there's an algorithm called BFGS. The reason people use it is it's fantastic. If you are like if you're trying an optimization problem and you're not really sure what works yet, you should just use BFGS. It's amazing. It's a first order method, sort of. It's using evaluations of the function and its gradient to sort of take local steps around, but it's also trying to do this in such a way that it also approximates the Hessian. And so it's one of these like quasi-Newton methods where you don't waste the time in trying to compute the Hessian every time, so try and approximate it as you trudge along the landscape. And yeah, it has a bunch of other like souped up features that makes it like really useful. It has all sorts of like tricks about like exactly what step sizes it takes and how to manage that. So yeah, it's just a fantastic algorithm. Very cool. And it has some nice variants. So yeah, the LBFGS. The L stands for limited memory. So this basically, now it's approximating the Hessian as it goes along, but it only updates the Hessians like every once in a while. And that helps you save memory by not like storing the Hessian from like all the previous steps and trying to like approximate it the whole way. So you can sort of reduce your memory usage that way. And then there's also LBFGS-B, what B stands for bounds. And that lets you do this algorithm, but with constraints. So it's a very multi-purpose tool.
Very cool.
Yeah, great question.
So, as you mentioned, if you have the same, if you compare two configurations, if one has lower QS error, it's going to generally have better confinement. And if you have the same stage one configuration and you compare two coils, if you have better B.N error on one than the other, that means that you're generally going to have better flux surfaces, and that will also have better confinement. Is there really, besides just tracing the particles, is there a way to compare like the mix between that? So like you have two coils from two different coil sets where you know like the stage one's kind of, the stage two of that kind of, but like mixing those two.
No, it's hard to figure out because even quasi-symmetry doesn't guarantee perfect confinement, right? Like you still, at the end of the day, there can still be differences between perfect quasi-symmetry and like if you do Monte Carlo directly with and look at the fusion alpha losses. So there's still subtle differences there, and like how that also trickles down to like errors in coils and exactly what those errors are. So for instance, some coil errors will degrade your quasi-symmetry more than other coil errors. So the story is very complicated. I think it's hard to say anything in general.
On the last slide, you talk about like the open problem in
Yeah.
coil topology. I was wondering whether it's, I guess we would expect for the coils and assume that the coils have uniform density, like uniform thickness, or how do we go about encoding that into the problem?
Yeah, the short answer is it's very challenging to let the coil topology be optimized. But for the filaments you saw, you have to describe a curve in space, and you don't want that to intersect with the plasma or with other coils. And often that prevents like topology changes where a coil was interlinked with plasma, and like at the end it's not interlinked with the plasma, would have to through the plasma. So it's challenging to sort of figure out how to do that with some of these existing methods. Maybe I'll show a brief slide of a crazy thing Matt and I tried with these voxels. I think I have a slide on this. Oh, actually, I might not have it on this. Okay. Yeah. So one thing we did try is go back to this. Is we basically just initialized a big 3D volume of like cubes of current, and then we just optimized what those currents should be, and like before optimization, there's no coil topology choice. We just basically like let the currents evolve and minimize the be normal on the plasma surface, and we were able to get like pretty cool looking topologies, but that has its own challenges because now you have to optimize this like very complicated looking, really it's kind of like the winding surface method, but instead of a surface, you're now optimizing like a whole volume of currents, and that has its own complications. So yeah, it looks a bit like this, but instead of this winding surface, we have this very complicated volume to deal with. So there's some initial ideas on that, but it's hard.
Yeah, small follow-up. If you imagine them as voxels, it's kind of similar to like like in the Muse setup where you have permanent magnets and those are all that cool.
Yeah, it's similar in spirit, absolutely. The difference is the magnets are all self-contained. Each magnet just produces its own field. To leading order, there's no interaction between the magnets. And for the voxels, the currents are flowing between all these cubes. You actually have like currents flowing through everything.
Last follow-up.
Okay.
How do you discretize those voxels?
Yeah, I mean we basically just put little cubes. We take a big volume, discretize it into little cubes, and then we basically do splines to represent the current in each of those cubes. And then we have certain conditions that allows the current to flow. But for instance, like div J has to be 0. There's some constraints. Send you the paper if you want, but there's some details there.
Thank you.
Okay. Yes, Sienna.
Yeah, so I was kind of interested you mentioned ever so slightly about optimizing for some like discrete quantities, like number of field periods, and you said that is typically not done, but still caught my attention just because I realized like there are a number of quantities that we could optimize for, like for instance, even just number of coils per field period, because there are a lot of trade-offs in that as well. But also, of course, you're not going to be dealing with continuous gradients, so that's going to be a big challenge. And I was curious if you know much about like how people actually have optimized for discrete quantities like this in the past, and
Yeah.
like what are some of the challenges or advantages associated with this?
Yeah, so I don't know how you would like so one thing you can do is just turn off the discrete symmetries. So in other words, you can like design a stellarator that does not have field period symmetry and does not have this up-down stellarator symmetry. And that's perfectly fine. The reason we often don't is actually one of convenience, which is what is really nice, go all the way back here. What is really nice about these is because they have this rotational symmetry, all you need to do is design the plasma for this unique slice. And similarly, you only need the coils for this unique slice. And then everything you just gets rotationally symmetrized around. And that means your optimization problems are a lot lower dimensional, a lot easier to solve potentially. So this is like field period symmetry. It does have some physical consequences for the plasma, but for optimization, it's also extremely useful to just like reduce the dimension of the problem. So yeah, some people have looked at like one field period, no stellarator symmetry, but then the optimization problem is just like much bigger. But yeah, there might be some cool stellarators out there. Pretty cool. Yeah. Okay, last one. I've ran extremely long. So.
Yeah.
Can you optimize the currents using regular coil optimization method?
I say that again.
Can we optimize the coil currents when we use the winding surface?
Yeah, that is the target of the optimization. So I told you we're gonna choose this current potential. Back here. Yeah, so the minimization problem is choose a distribution of the current potential on that surface to minimize these objectives. But remember, the current potential is just straightforwardly related to the current. So really what you're doing is exactly what you said. You're choosing a distribution of that sheet current on that surface. And you're choosing that distribution to minimize these.
You mean that we can choose the different currents for the different coils?
Well, so you're optimizing this. So forget about the coils for a second. Coils don't appear in the winding surface problem. You just have this green surface. You just choose a distribution of currents on that surface. That gives you a good solution. But now when you actually want to build a device, you have to somehow figure out how do I actually get coils from this continuous sheet current. And there's some prescription of basically finding a way to get coils from this continuous sheet current that sort of doesn't give you huge errors. It'll give you a little bit of errors because it's now a discrete set of coils. But this is really like a post-processing thing. The optimization problem itself, there's no coils here. It's just continuous sheet current. Great. Okay.
All right. Yeah. All right. Let's give our speaker. Been great that we're getting a lot of questions and engagement, but let's take a bit of a break. We'll